Last talk by Philipp Jacobsohn. Philipp held management and technical position at very well-known worldwide digital electronics firms such as Synopsys, Simplicity, and Lattice Semiconductors. Now, Philipp is a principal application engineer at SmartDV, where he supports the users of design IPs and verification IPs across continents. Moreover, he is a technical writer, very keen on sharing his knowledge. So today, he presents error-redundant implementation of IP cores with a practical example of a PSI5 Controller IP.
Thank you. And switching is, how does it work?
I haven't used it yet.
Okay.
This is the pointer.
This is the pointer, but switching from slide to slide is, okay, excellent. Okay. Last presentation for today. Thank you very much for staying so late. Let me quickly introduce myself. So my name is Philipp Jacobsohn. I'm employed as a principal application engineer with SmartDV. SmartDV might not be known to you guys. So we are a provider of digital IP, so verification IP as well as design IP with a focus on interfaces. So whenever you would need some kind of PCI or USB or SD or whatsoever, when it comes to interfaces, SmartDV would be your partner. Okay, so let's move ahead. The reuse of predefined functionality has been a standard methodology since many years. There are tangible technical and commercial reasons for deploying IP cores rather than developing it by yourself. However, this shall not be discussed during today's presentation because it is simply assumed common knowledge. Let's have a look from a different angle. Typically, IP cores are developed with a focus on commercial applications. Secondly, the typical target device for IP cores are ASICs, not FPGAs. So what need to be considered when it comes to the FPGA as a target device will be discussed in detail during today's presentation. In order to appropriately respond to the functional safety requirement, it firstly must be determined where the IP core will be deployed. Based on this information, it is possible to decide what kind of errors might occur in a system. Here we have to distinguish between systematic errors and random errors. Systematic errors can be ruled out typically by increasing the verification coverage or deploying advanced verification techniques. I would like to emphasize the use of verification IP because this allows us to increase verification coverage and code coverage dramatically. Other topics such as human error or mistakes in circuit development can be simply ruled out by deploying silicon-proven IP cores. When it comes to random errors, one must consider that an IP core was not developed with a focus on functional safety. As said, typically IP cores are developed for commercial applications, and under that perspective, it is very important to understand that the IP vendor has the ability to write the RTL code in compliance with error detection and correction circuits. Typically, so these are TMR, triple mode redundancy, as well as ECC. There are also some other techniques in order to improve the reliability of a circuit, and specifically here for an IP function. The next step would be to categorize the IP in terms of requirements and, in the first instance, the probability of a failure. Okay. So for example, IP core that is used in an automotive environment has much stricter rules rather than an IP core that is used maybe in a commercial application. In order to categorize, we must make sure to define the safety requirements, the probability of failures, the consequences of failures. We must define how we can prevent failures, and if it is not possible at all to prevent those failures, how to react on them. Okay? So this categorization is being done with safety integrity levels. Typically, this would be SIL 0 to SIL 4. And when it comes to automotive application, ASIL-A to ASIL-D or mil-error applications. With the SIL 0, the lowest safety strategy, and the higher the number, the higher the strategy. Okay. So let's discuss how to deploy an IP core. So typically, IP cores are developed by the IP vendor, but not certified in any way. And the reason is that typically, as a whole product is running through a certification process, and the IP core that was purchased and embedded into the application will be certified as a part of a complex project. Still, it is necessary that the IP vendor respects during the development of the IP core that certain requirements apply. For example, to make sure that the documentation on bugs and assumptions is documented very well. And now let's come to a little reality check. I believe that this is a very important topic because typically when an IP core is purchased, it is assumed that this is a plug-and-play solution. A plug-and-play solution that allows you to import FPGA optimized RTL code, optimized for either power consumption, performance, or also area. But here, we have to face a situation that the IP core was developed typically for ASIC structures, not for FPGA. And this, in the real world, makes it necessary to apply modifications to the RTL code. So these modifications can be applied by the IP vendor itself or by the appropriate user, dependent on the requirements. For the modifications, typically these have to be applied on memories, on I/O structures, as well as on clocking structures, because these are the topics where we can see differences between an ASIC and an FPGA implementation. Okay? Further topics where it becomes complicated are, for example, ASIC library instantiations. So you purchase an IP core that contains certain instantiations from ASIC libraries, which are obviously not compliant with the FPGA flow. The next topic is a quite important one, and this is regarding FPGA performance. So the FPGA performance is typically much reduced compared to an ASIC device. But if you now purchase an IP core that is originally targeted for ASIC, it might happen that it just cannot run at speed when being ported to the FPGA. So you have to make sure that the IP core that you purchase from a third party or that you deploy from a third party is already tested on FPGA targets. The last bullet that we see here is regarding the tool environment. As ASIC IP cores are typically synthesized with ASIC synthesis tools such as a Synopsys design compiler or Cadence tools, they might cause issues when being run through FPGA synthesis. Also, this has to be taken account. And this little reality check that we are doing here gives us the answer that it is not as easy as one would expect to import an IP core that was originally developed for ASIC and now is ported to the FPGA structure. The considerations to make when purchasing IP cores or deploying IP cores is listed here. When it comes to third-party IP, the first question that we have to ask is about area utilization and performance. So was the FPGA already tested, or was the IP core tested with specific FPGA structures? Is the area utilization still possible? So is it possible to map the IP to the specific FPGA or not? When it comes to power consumption dissipation, this typically leads to the question, were specific clock structures included in the design to lower the power dissipation, so these would not apply to FPGAs. And the last topic here is about test structures. So typically ASIC designs contain design for test structures that must be removed for the FPGA implementation. Okay. Then the next topic to discuss is when porting such a FPGA IP core, we need to understand which FPGA or which FPGA platform to deploy. Let's make a practical example here. So given the fact you want to import a PCIe core Gen 5, Gen 6, okay? Now you have to choose a proper FPGA. So obviously this would not be a low-cost FPGA from any vendor because you could expect timing and also area issues. Okay. The next topic is about choosing the right EDA tools, and also you have to check the availability of RTL code. Okay. The next topic we already discussed briefly, so we do not offer a plug-and-play solution typically for ASIC cores. You must consider this will cause time and efforts on your side to convert existing ASIC cores to make it suitable for FPGA. Next topic is about gate count. We have discussed this, but also the next topic is quite important. Quite a few IP cores require not only the digital part of you, obviously, but also the external PHY. Okay, in an ASIC, it's not an issue. You can use an analog function that can be put on the same die. But when it comes to the FPGA implementation, you will need an external PHY component, and you must make sure that this PHY component will work seamlessly with the digital IP. The next topic is about the, I would call it the ugly three. The ugly three, because these are typically the differences between an ASIC and an FPGA implementation. Typically, you see differences in memories, I/O pads, and clocking. So if you take a look on a specific ASIC RTL code, you will see large register arrays that are mapped as memories. If you would try the same to do with an FPGA, you will quickly run out of resources. The next topic is about specific FPGA optimizations also need to be considered because when you target an FPGA, it might be necessary, for example, to introduce maybe additional registers for retiming to increase performance, so things that are not included in the original ASIC code. The next topic is about constraints. So when you get an IP core, you not only get the RTL code, but also suitable constraints. But these constraints might not apply properly to the FPGA. Okay? So some adjustment is typically necessary to make an FPGA working with an ASIC IP core. Then when it comes to clocking, this is a major difference between ASIC and FPGA structures. The clocking structure must be suitable and typically also must be adjusted to suit the FPGA clocking. Then, regarding recommendations, obviously as an IP core vendor, you are asked to have as few changes as possible in terms of RTL code. So the RTL code should be suitable for both architectures, for the ASIC as well as the FPGA. So whenever possible, apply as few changes as possible. And this is a request that we typically get. Okay. Then the next question is about the physical interface, so the external PHY. It should be tested, and you should make sure that when you get an IP core that requires an external PHY, that this is tested and also validated in hardware. So, what else should design teams bear in mind? In some cases, it is required to reduce the functionality. A typical example here is PCIe interface that is working seamlessly as a 4-lane interface on an ASIC. If you would like to do the same on FPGA, it might be necessary to narrow it down to just 1 lane, because otherwise it might not be possible to port it to FPGA at all. So let's come to a practical IP core that we have provided to one of our customers recently. It is a PSI5 interface IP. Not sure if you have been involved in this IP previously, just a brief information about it. So PSI5 was originally developed as an interface for airbag systems in cars. It is a very robust and very simple interface. It's just a 2-wire interface with unshielded wires, where the 2 wires are both for power supply and as well as data communication. So this PSI5 interface has been developed at SmartDV with the request for ASIL-B compliance recently. And it has some features that are commonly used in the industry right now. It also has some limitations. For example, it just offers a 125 kilobit per second data rate possibility and maximum quiescent current of 50 milliamps, unidirectional data transmission, but it has also quite a few advantages because it is really a robust and very cost-sensitive interface. So the SmartDV implementation is a pure RTL design, so we deliver that design in plain Verilog, human-readable Verilog. It's very easy synthesizable to both ASIC as well as FPGA. And when it comes to functional safety requirements, we offer both ASIL-B as well as ASIL-D compliance with that IP. For the implementation, we have chosen SEOCC flow. SEOCC means safety element out of context. So the safety element means that it will be used in safety critical applications. So we know about this. And the out of context here means that we know that it will be in safety implementation, but we don't know in which and what is the categorization. Will it be ASIL-D? Will it be ASIL-B? We don't have any clue where it will be used. Okay. So in order to comply with the ASIL-B certification or compliance, we have adjusted the RTL code. So you can see in the upper window RTL code that does not contain any safety critical implementation. As you can see in the picture below, the effort to make it ASIL-B compliant was quite drastic. There are different fault categories implemented, including error code correction. We have implemented watchdog timers. We have implemented CSR, so special purpose registers with parity. as it was only ASIL-B and not ASIL-D required, some additional features such as TMR have not been implemented. Okay, so this is already the last slide. Just would like to quickly have an overview on verification and design IP that is being offered by SmartDV. We just see here a snapshot of all the available functions, but these are the ones that are typically used in functional safety requirements. We offer a lot more. But these are the ones that are used in, for example, mil-aero or defense applications and automotive applications. Yeah, might be of interest for you guys here as well. I would also like to emphasize the use of verification IP. So SmartDV was starting off with verification IP. The design IP portfolio just came later. And verification IP offers you with advantages to accelerate the overall verification process and also to make sure to randomize tests, to have much more tests in the same duration that you would have when just using, I would say, test benches or other verification methodologies. Okay, thanks a lot.
Thank you, Philipp. Are there any questions for Philipp? If not, I would like to ask one myself. So concerning the wide portfolio of design and verification IP, what kind of tool chain, tool syntax, and verification methodology would you normally use?
Yeah, thanks a lot for the question. So as said, we have two different portfolios. So one is the design IP that is developed in plain Verilog RTL. With the design IP, you will always get a test bench. You will always get sample code, you will get constraint and appropriate reports. When it comes to the verification IP, this is much more comprehensive deliverables, so you will get full test cases with randomization and a lot of test scenarios that are delivered together with the VIP.
Okay. Interesting, thank you. Okay, I don't see any other questions? Then we can thank Philipp again.
Thanks a lot.